So, hi everyone. Today we're gonna learn about um, basically the second important thing for math um, programming in Python. You want plots, right? So let's start. Start from the very beginning. So let's import NumPy as NP.
We cannot see your screen.
Ah, okay, sure. Mm, share desktop. Okay.
Yes.
Let's start with importing NumPy as NumPy NP, like last class. So today we're gonna continue with the next library, which is Matplotlib, very useful for plotting graphs. So we have Matplotlib, and then we do dot pyplot. So we only need that part as PLT. This is a very common way to import this package, this module. Okay, so let me show you one interesting thing. Is in NumPy we have a linspace, so which is quite similar to arrange. Last time we learned NumPy.arrange, which was the start, stop, and the step, and it will give you a list of numbers between the start and stop with the amount of step. But this time we want I'll show you linspace. The difference is it will be start, stop, and not the step, but the size of the step. So for example, if you say we start at 0 and we end at, let's say 1, and we can divide 0 to 1 by a step of, let's say 1,000 steps. So here it's start, stop, and then step size basically. So if you do this, you can print out X, and it's basically all the numbers from 0 all the way till 1. Looks like 1 is inclusive, and we have divided into 1,000 parts. We can print out the length of X. Yeah, so we have 1,000 elements and the start, basically the number of points. Okay, so this will be helpful. Okay, so let's say instead of going from 0 to 1, let's go to 0 to 2 pi, right? So what you do is the 0 and then 2 times numpy dot pi. This is a constant that's part of the numpy, which is 3.1214, whatever, as you know. But if you do numpy dot pi, it's going to be more precise, right? We will have many more digits. Okay, and we can define y, and let's just make a sine graph. So it's very easy. We just do numpy dot sine because numpy has sine function already, and we just do this. So y equals sine x, as simple as that. And now the interesting thing is we can do plot dot plot y. So simply this will plot the y. However, there are some problems with this plot. Is the x-axis is unknown. We don't know. So if you just give y, it will put the number of the points, like which point it is as the x-axis. So usually what so if you have only like one array of numbers you want to plot, you could just do plot y. But you can do plot x, y. Then now it will actually be correctly displaying the x value, which is going from 0 to 6.28, right? And then the y-axis is the sine graph of the x. So just by doing, so it's quite simple to plot graphs of sine. You can easily change it to cosine, right? And maybe tangent, but tangent has a little problem, right? Let's see. Okay, not too bad. As you know, tangent goes to like infinity at some points. All right, so that's how you plot. Quite easy. So, but we can improve the plots. But before this, if you're just using Python without Jupyter Notebook, you may need to do plot figure. So this one says that we are starting a new figure, and then the next one says plot.show, and this will means we will show the figure simply. So basically, we do plot.figure to create one figure, and then we plot, add the line on the plot basically, and then we show it. We can even do nice stuff like plot dot save fig. You can even just do this and something like this, and this will create the PNG image that you can download and use in your scientific paper, right? You can plot your graph. So, but check this yourself. So, can save figure, and it will be saved in the folder that you're running your Jupyter Notebook. Okay, so what else can we do is we can modify the plot, how it looks. So for example, let's just decrease the number of points so it's a bit easier to see. Let's say we have 50 points, and it's still like a straight line, but if you zoom in, it's actually like, what it does is it basically connects all the points. But if we want to make sure that this is a point, everything is a point, and don't connect all the points together, then we can specify these additional things. So plot x, y, and then specify this. Then this will be like a dot. You can change the color of the dot. B is, I think, is blue, right? So B dot gives you this blue graph. Maybe like G will be green, etc. You can Google this. Yeah, you can Google what color you can add. You can even specify exactly what color in terms of hexadecimal value, etc. Okay, and not only this, you can add like this. And this means you have a dot, and all of this will be connected by a line, and it exactly does what I did. Basically, G specifies it's going to be green. A dot is specifying each dot is a dot, and this line shows that we're going to connect everything by line. And we have another like small o, then it's like a bigger point, dot is like a smaller point, and all this stuff. Let me show you how you can add second plot like a second line on top of this line, I think you can do it several different ways. Let's do y2 is numpy sine of x. Okay. So how can we add this? We can probably do this. Yeah. Quite simple. So in the plot, we say, let's plot one more line. We have x and then y2. And y2 is the sine graph. Y is the cosine graph. And now we can make our plot nicer. If you're using this for some scientific paper and stuff, you want to add x label. And you can call it x, right? We can say plot y label, and then we can call it y. So we just added x here and y here, or we can name it differently, right? X values, y values, however you like. So that's how you can do graphing using the Python and NumPy and Matplotlib. Super easy. And you can add title, I think. Sine and cosine. Here I have sine and cos. And you can add a legend. And legend, I think, is added with a list and with a name. So name is going to be within quotation marks because it's going to be string. So the first graph is the y, and that was the cosine. So let's name this the cosine graph. And let's name the other one sine graph. And we added a legend here. Cosine graph is the green with the dot, and the sine graph is this light blue color. And of course, you can, however you want, you can change the second one into just dots or just maybe O. You have this. You have a lot of freedom to do whatever you want to plot nice graphs. All right. So that's one good thing to know, learning how to plot. So I taught you a lot of the basic coding stuff already. And today I can show you just one example of how you can use like Python to solve math problems. So let's work on Newton-Raphson method. You have learned about it. Basically, a Newton-Raphson method is a numerical way of solving a problem. So imagine you have like some kind of function, and we want to find the root of the function. So where it's equal to 0. But let's say you don't know this exact value. What we do in Newton-Raphson method is we can guess with some initial guess and then iteratively improve this guess and get closer and closer to the real solution. What we do is we go to the initial our guess, and then we approximate our function with a straight line. And how do you approximate this straight line? Is of course we just use the first derivative and make the function like linearize the function. and we can find the zero for that linearized version, and we do the same here, and iteratively it gets closer and closer to the resolution. So numerical methods are basically always going to be like approximate answers, but you can approximate as much as you can get as close as you want. Okay, so this rule ends up being a simple rule, iterative rule. Well, x is going to be the prior x minus the function divided by its derivative, evaluate at the prior points. So let's think of some nice function. Maybe like x plus sine x, something like that. Let me try out. Say x is numpy dot in space 0 to 2 pi numpy dot pi. I think you can even do this. So numpy will piecewise or like element-wise apply the sine function onto our tons of x's, and then element-wise add, and then we'll get y. Let's plot this. Okay, what kind of function can be nice, which will reach 0, I guess cosine. So don't want to use my brain so much. Let's say we have this function 2 times numpy dot cosine minus x, and we're trying to solve this function equal to 0, or we're trying to find. So if you think about it, any function, any equation you can write in this form, right? If you have like f equals g kind of function, you can always just write it as f minus g equals to 0. So this means we can convert any equation, any single variable equation, into a form of something equals to 0. And we're just trying to, and that will be used as our main function. So let's say in this case, we want to solve something like cosine 2 times cosine x was equal to x, and assume x is in the radians. So we want to solve this. Then we can move x to the other side and make this function, and then we try to find a 0. So you can look at the graph and approximately tell this, okay, this is something like 1.2 or whatever. That will give you 0, but you want the exact answer, or as close as possible. So let's implement a Newton-Raphson method to solve this problem. That would be, so what we can do is define our function f as give the x value and return, right? 2 times numpy dot cosine x minus x. That's our function. And in Newton-Raphson method, there's 2 different ways of solving this. If you know the analytical way of finding a derivative, then you can just define it yourself, like define f prime equals cosine derivative is minus sine, so return minus 2 times numpy sine x minus 1, right? So this would be the prime, the derivative. You can define it like this, or there is one more way you can do it approximately, would be just you can do like define. Basically, what you can do is use our f function sub and apply, you know, a small amount of so let's say h equals 0.001 or something. So I can add the small h minus this divide by h. So this is basically how you do derivative approximately, right? By using the fundamental derivative equation. I forgot what's the name. But instead of going putting a limit and h goes to 0, we can't do that numerically. So we just choose a small step and then we evaluate the function a bit later, subtract it, divide by h. And I'm sure you all know. So let's go it this way. Let's try out if this works out. Let's first check if the function is working. So let's try to print f of 1. And this gives you some value. Let's print out f prime of 1. Okay, so it works as well. So perfect. So Python is so nice because you can see this is almost just like writing down this math equation. It's not very complicated, very easy. So now we have the function and the function derivative. Let's iteratively solve this. So what we can do is use a while loop and okay, let me just show you the easy way for now. We can use a for loop and say we wanna iterate 100 times, right? So in 100 times, what are we gonna do? Before the for loop, let's initialize our x. I'm gonna initialize x at 2. So we're gonna start here, but we're trying to find the root at 0. So we can start at 2, and then we slowly get closer using the Newton-Raphson method. So this is how I initialize x. And we're gonna update. So x is gonna be prior x minus f of x divided by f prime of x. So it's simply you can think of like this is the function value, and then this is the derivative, and you divide that, you kind of get approximately how far you're away from that 0. if this was a straight line, we would just find x instantly. However, since this function is not straight line, then it will take several iterations to reach the value. And then we print out the x. And let's also print out the f of x. So what this means is x is now gonna be the value that's closest to the root, and f of x is supposed to be close to 0. So perfect. So our solution is quite easy. X is equal to 1.0298, all this number. And then our fx is 0.0. And let's see how this would have changed if we start with just the 1. Okay. Okay. What this means is if we did only one iteration. So we start at 2 in one iteration. Our x would have been 0.99, and then our root, basically this is supposed to be 0, but now it's 0.09. So it's gonna get closer and closer. If you instead did like 5 iterations, this is already a super small number. It's very close to 0, and this is the solution to the x. So that will be how you can implement Newton-Raphson method in Python and solve a function root. Okay. We can probably visualize this as well. So this is the very basic code, but if you want to visualize this, you want to save all the x's, right? And so let me show you. What we can do is we can say x is actually a numpy of empty, and we're gonna do let's just say 10 iterations, right? So this is the size of the empty, if you remember. I think this works. And x of 0, the first element, I'm gonna start initializing with 2 as before. And in this, I'm just gonna copy this for loop. Instead of working with the same x, you're actually gonna work with the prior x. And then this will be the next x, I plus 1. So if you think about the for loop starts at 0, ends at 4 inclusive, because 5 is not included. So what we're gonna do is x0 minus f of x0 divided by prime f of x0, and then equals x of like the next element, x1. And then I is going to increase by 1, then it's x of 2, etc. So why am I doing this? Is because now we have all the numbers of x starting from the 2 to the final solution. So what we can do is we can again make a plot to show how our answer is going to get closer and closer to the root, basically. So plot figure, plot show, go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah, this should be the same number. So 10 is out of bound. Okay, if you do 10, this ends up basically doing one more unnecessary step. So this should be 9. So that means we have x has 10 values. And then we do 9 steps because the first one is already given, and then 9 times we progress our x. That's why this difference between 10 and 9. Or you can, a lot of times, you can say n is the number of iteration, and then we call it 10, and then we say this is empty of n. This is range of n minus 1. What does it accomplish is it will make your code easier to modify later. So this is it's going to change nothing, but if you just say now, instead of 10 steps, let's do 100 iteration and code will instantly do it. Or if you say, let's just do 2 steps or 3 steps, the code is going to do it as well. So let me show you just 5 steps. So x is starting at 2, and then our x is getting closer and closer to that value. Let's save the corresponding y values as well, so that it could be easy to visualize, right? So that you can visualize it in a different way. So then we can define numpy empty. So we basically create an empty box to hold our y values first. And our y of 0 is gonna be f of x of 0. And in our for loop, what we can do is we can do y of, no, actually it's the same. I plus 1. You can think of it in 2 different ways. We can do it in the same for loop, or we can apply another for loop, and I think that will be slightly easier to understand. So let's say we already have the x values. Let's just find out the corresponding y values. Then all we have to do is every y value is depending on the x value. So we can simply do this, right? So y equals f of x for every single y value. And we can plot the second plot. Let's plot another plot where it's actually x versus the y. So you can see that we have this point and this. It's easier to see what's going on if we have a dot. So with just a few steps, we start from here, and then one step we went all the way here, and then now we're here. And let's overlay these with the original this function, so it's a bit easier to see. So what we can do is here, I'm going to define x2 So I'm just going to call these two different names because if you say x equals to this, y equals to that, then we're going to lose our calculated these values. So x2 equals numpy linspace, blah, blah, blah. Y2 is like this. And we're just going to plot these guys together. One additional thing, actually, you can plot it in the same line as well. Yep. So just to show you that there exists other ways of doing this. X and Y must have same dimension. So there's some problem with dimension. Yes, this is supposed to be X2. So now, what did we do? Let's summarize what we just did. So basically, we had defined, I first showed you the function. So I first showed you in this x is just saying x is going to go from 0 to 2 pi with 100 points. And then y is going to be 2 times cosine minus x. And we want to find out where it crosses 0. And to do that, we define the Newton-Raphson method, where we define the function as a function, f of x. And then we define the prime by simply subtracting and dividing by the step and using a small step. And here we have done 5 steps of Newton-Raphson method and plotted how the x went from 2 to all the way to 1.003, something like that. And here I'm showing you on the original graph, compared to the original graph, where we start with the guess of 2. And then within one step, we went all the way to 1. And then the next step, we got really close. And after that, our human eyes cannot distinguish how close this is to 0. But if you just print out the final value of our x1 trick, since n is the maximum number, and it goes from 0 to n minus 1, because we have n number of elements, and then the indexing starts from 0, so the final index must be n minus 1. Or the cool thing is actually you can do -1 indexing. What it does is we index from the behind if you do negative indexing. So anyway, now I'm printing out the x, and we got 1.03, basically. That's how we do Newton-Raphson method. So I just showed you how to plot a figure in Python using matplotlib, and how you can combine matplotlib and NumPy to do all sorts of calculation and all this. So in terms of Python programming, this is Python programming for math people. This is 90% of what you need. From the first lesson until here, we have covered a lot of different stuff like if else, for loop, while, arrays, and now NumPy and matplotlib. And of course, you can look for more stuff. And if you're interested, you can learn about object-oriented programming. But honestly, object-oriented programming is not that much used NumPy if you just want to do math calculations. And I rarely use it personally. Yep. So that's about it for my tutorial. So at home, please please play with the graphing, right? So play and figure out how you can plot nice graphs like this, and then save that, and you can use in your scientific papers. I use this all the time, this kind of graphs. Already looks a good quality for paper. And additionally, what you can try is something like binary way of finding a function root. There's another way of finding a function root. You don't have to know the derivative, and it's works quite well. I think it's called binomial method or something like this, binary method. Yep. So after this, it's really just your creativity. Like, how creative are you? How can you, what you want to do? You can use all the tools I showed you, and you can do a lot of different stuff with just the basics, if, else, for, while, graphs, and NumPy. That's all you need for math coding, really. Right, so that's about it.
Yeah, perfect. Thank you very much, Mr. Bhatt.
You're welcome.
Today marks the conclusion of our Python course, proudly presented by Mathematics Media. And we are very heartful. Thankful to you, Mr. Bhatt, from the Max Planck, Germany, to delivering the very nice lecture on the Python course. Thank you very much once again. And I am also a special thanks to the Mr. Dishan for these organizations for this course. Thank you, Mr. Dishan. And I also appreciate the participation from all attendees who give the full interest and engagement on this course. And thanks to all. Yes, thank you very much, Mr. Bhatt.
You're welcome.
Zishan, are you here? Zishan? Just one moment. Yes. Zishan, can you hear me?
Yeah, I can hear you.
Yeah. Okay.
Hello, Bart. How are you?
Good.
Yeah, thank you so much, bro. We a lot of learning from your side. We really appreciate. I think every Pakistani will proud of you. Thanks for your time. Like I can understand how busy you are, and nowadays I think the poster week in Max Planck also. So
yeah.
I really appreciate your time. Thank you so much from all of Pakistan, from all the students, and hopefully you also enjoyed.
That was
Actually,
pretty interesting.
we will apologize for the low participants sometime, because sometimes people or students are busy, so we also send students to the recording of the lecture, so usually they
exactly
learn from recording, so that's why.
Sounds good. Yeah, I tried to give all the basic overview of the Python, but really is all you need.
And one more thing,
Sure.
we are eagerly waiting to host you in Estonia, Paris, Italy, or Pakistan.
Yeah,
So
yeah,
you will
exactly.
choose. So
Always
you will
welcome to
choose
Paris and always welcome to Estonia.
Italy and anywhere. But I
Exactly.
wish like you will visit Pakistan.
Uh-huh.
Yeah,
Maybe someday.
yeah,
Yeah,
of course, we will
of
plan
course.
something so that you can visit.
Yeah. Thank you
All
very
right.
much once again, Mr. Bhatt, because it was a free course on Python, and we try to organize in such a a great way. But sometimes, exactly as Ishan is saying, sometimes the participants are very busy, or like in Pakistan, the time is 9 p.m. Maybe sometimes the participant is difficult to join us, and they are joining us on recording maybe.
Sure.
So thanks a lot. See you maybe in Germany and in Max Planck's. Thank you very much.
All
Thank
right.
you. Bye.
You're welcome. Thank
Thank
you,
you very
everyone.
much, Zishan.
Bye.
Bye.
Yeah. Welcome, Jawad. Welcome. Thank you, Jawad. Okay. Okay. Bye.